This formulation is due to Ravel and Swain back in 70. That's the initial formulation. And it's an adaptation of Balinsky's problem or integer programming formulation for fixed charge problem. So which is even older. Okay, these are old stuff. When I was doing my doctoral, Ralph Swain was at the University of Florida. He was actually he happened to be on my doctoral committee during the defense. Thank God he didn't ask too difficult questions. And Ravel, he's a quite well-known person in the location circles, but unfortunately he passed away last year. But he's quite well known with many contributions. All right, so the formulation they came up with is the following one. You minimize the summation Cij Xij, where Xij is a 0-1 variable. It will be 1 if the ith vertex receives service from a facility at the jth vertex. That's the definition. So you're summing this over all ij pairs, okay? Subject to, we have one condition which says that summation Xij over j is equal to 1. J going from 1 to n, if you want to do that. Let me do this also, double summation, I going from 1 to n, j going from 1 to n. Cij is the distance between vertex I and j, or cost, the least cost, okay? All right, so this is written for each I. And what does it do? The ith vertex must be assigned to at least one facility at one of the possible locations, okay? And you also have Xij less than or equal to Xjj for each ij pair. Now, Xjj will be 1 if you place a facility at the jth vertex. And if, for example, Xjj is equal to 0, then you cannot assign any I to j. That's what it forces to, okay? But if it's 1, then you may or may not want to assign I to j whenever there's a facility. And finally, summation Xjj, j going from 1 to n, is equal to the fixed number p. So you're choosing p out of n vertices by forcing this constraint. And Xij's are 0 or 1. Simple formulation. It works. And what Charles Swain did in his dissertation, Ravel was his actually PhD advisor, so you know sometimes things are this way. Okay, so in his dissertation, Ravel looked at this problem. He solved it as a linear programming relaxation, and then he observed that most of the time he is getting integer solutions, which was good. But from time to time, he was getting fractional solutions with 1/2 for certain Xij's. And that, of course, At that time, these integer programming techniques were not polished enough yet, so he had to do some. He had to apply some either. He used some branch and bound just by branching over fractional variables, and it usually turned out that in one or two branchings he obtained the integer solution. So it was a successful way of formulating the p-median problem. And later on, people also formulated this, or people observed that this problem has a very similar structure to the very well-known incapacitated facility location problem, UFLP. You might have heard of that maybe in other courses. Incapacitated facility location problem has costs of assigning the ith facility to the jth facility, and these xij's could be fractional. You may be assigning a fraction of the demand to the jth one, and that would be the cost of assigning I to the j. So in this case, we may take it to be wi times dij, so to speak. There are also fixed charges, which is another summation here with fj times, say, yj, where yj, or xjj in this notation, where if you're placing a facility at the jth vertex, there's a fixed charge of doing that. Okay? So let me just give that. Sure. Mm-hmm.
Instead of equality greater than,
Mm-hmm.
we would be satisfying the requirements, and the objective function would minimize the
Yes. Mm-hmm. You can do that. I don't think it would hurt the solution. It would relax. So if this is, for example, 2, that means actually your facility I could be receiving service from either one or the other. But normally, because of the optimization, yes, if Cij's are positive numbers, it won't do that. Okay, so you can certainly relax it to inequality, greater or equal type inequality. And actually, with integer programming problems, you never know how small changes will affect your solution times, or maybe the characterization of the polytope of the integer solutions here. So sometimes it's good to play with such constraints, actually. Equalities are usually harder to deal with in integer programming than inequalities because of the way I think Cplex works. We don't know the exact machinery behind Cplex because they keep it concealed. Nevertheless, of course, it does a lot of pre-processing as well as branching cut most of the time. So having them would be good. Likewise, this one. How would you replace it, or what would you replace it with? Less than or equal. Yeah, if you can achieve a particular cost with less number of facilities, fine, go ahead and do it. Why should you, have extras? Okay. All right. Okay, are you? You still have to assign somebody to each vertex. So
for positive Cij values, it will always open to maximum number of facilities because it will.
Will it?
If
Well, it may.
Jj is 0, then.
Or Cj is 0. Yeah.
And changing this equality with less than or equal to will not hurt the solution.
But can it give you a smaller number of facilities? Still optimal, no?
It can, but in an extreme case, when P is larger than the number of nodes.
Well, that's a special case. However, well,
because
yeah.
If the less than P solution is optimal, then you could have the same in P, but you could also.
I see what you're saying. You would have additional cost, yeah, because I see what you're saying. So if you have, say, Q facilities less than P and still obtain a particular cost here, if you add additional number of facilities, well, you don't have to assign anybody to them, though.
Yes.
See?
Just you can assign them to each.
In which case you would be reducing the cost. I see what you're saying. I see. Okay. 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 Yeah. Okay. Because of the absence of fixed charges, I guess that would be the situation. Good. See, I never really thought about these that much, because once you formulate it, it's almost, done, except maybe for large sizes, okay? There's always competition in the integer programming world or in the operations research world, where people try to solve larger and larger sized problems. And to my knowledge, the largest size problem solved using related techniques, not just the regular branching cut, it was due to Beasley. I think he solved something like 900 nodes or something. Let me see if I have it in my notes here. All right. Beasley in 85. Let me give these information to you. Let me put down a few things here before we go into the other stuff. Well, first of all, it's good for you to know that Kornejolz, Fisher, and Nemhauser, they solved back in 1977 the incapacitated facility location problem quite efficiently. Actually, the initial solution was developed by Erlen Cotter. He had a successful algorithm back in 1974 using dual ascent procedure, which is still well known and still utilized. And they made it quite efficient, and they explained it quite well in a different paper in Management Science, which is marked as an excellent paper of excellence, because it's so well written. And Kornejolz is a doctoral student of Nemhauser, just the story part. But they solved this incapacitated facility location, which I'm going to give here, okay, in relation to that. And then Mavrides in 79 generalized the p-median and solved it using incapacitated facility location plus LP relaxation, Lagrangian relaxation. Then you have Galvao, still another well-known person. He used the dual of the LP relaxation and branching bound. So this guy generalized the p-medium to a somewhat more general problem, and he used incapacitated facility location solution procedure plus Lagrangian relaxation. What you do actually is you take this constraint, you throw it into the objective function by multiplying with a multiplier lambda. So when you do that, that becomes, in a sense, the fixed charges associated with opening facilities. Actually, in this case, facilities all incur the same charge. That's why you restrict the number of facilities. Whereas when you throw it into the objective function, you don't restrict the number of facilities, but you try to balance the transportation or delivery costs with the opening costs. Okay. Anyway, Galvao used that, and let's see, Buffy and Karkazis In 80, they solved a problem that has 206 vertices and 45 facilities. They used, again, incapacitated facility location problem with variable fixed costs. The variability comes from the variability of the Lagrange multiplier here, okay? And adjust according to PM branching bound. So actually, that's what most people do. They just simply, because you have a good algorithm for the incapacitated facility location problem, they just make this problem look like the incapacitated facility location problem, and they try to benefit from the existing methodologies for that particular problem. All right. Next, Christofides and Beasley from the England school back in 82. They used Lagrangian relaxation, and they solved again up to n 200, up to n equals 200. But then Beasley, who's quite well known for his contributions to linear integer programming, the solution, the computational material he has provided, he improved this to 900, the former algorithm. With p equals 90. And to my knowledge, well, at least at the time I was doing this study back in 2004 and 5, at that time, this was the largest solved. Now, Ataberk is actually exploring if other people have actually done a better job with it. Have you come up with anything larger than this? The 22-year solution?
No, that was the 22-year solution was for something else. It was.
Oh, it wasn't for the p-median?
No, it was for something like flow-based problem, but.
I see. Okay, okay. So anyway, if we have something larger that's already solved, then Ataberk will report that, okay? Because I don't really have time to look into that right now.
I think one can easily solve like this big much problem with like Cplex.
Just standard off-the-shelf software, yes?
I think like 1000 would not be so hard.
Well, maybe try and see, because Beasley, well, in 85, this is 85, yeah, I forgot that.
Even using the same algorithm, you can just do it much better.
Could be. Because Cplex have been polished so well, you know, it's been doing quite well actually. So just using sort of brute force Cplex with no additional thing, you may come up with something larger. So Ataberk will report that, I guess. Huh? All right. Let me also mention Merchandani. Ojit and Wong. They used a nested dual approach, which is a combination of Lagrangian relaxation via Erlen-Cotter's dual ascent method. So this is basically Lagrangian relaxation combined with Erlen-Cotter's dual ascent. Erlen-Cotter, again, is the first guy who invented the method for incapacitated facility location problems back in 1974. All right, so there's a bibliography by Rees. You might have encountered that, published in 2005. This is an annotated bibliography on p-median solutions. Or solution methods, let's put it that way.
Although the Rees bibliography does not list many of these papers as examples.
Really?
Yes, actually only the Barbaros paper has been listed as an exact solution by Rees. The others are not listed in exact solutions or formulations. Maybe because they're older.
I don't know, but well, many of these guys also provide heuristic methods based on the exact methods that they proposed. So maybe that might be the reason. Okay, let me give you the fixed charge. The incapacitated facility location problem. In that one, you minimize the summation of the transportation costs, in which case we may replace them by Wi times dij's, or just multiply it with another constant if you wish, times xij, again I and summation on I and j, subject to, in this case, xij is permitted to be fractional. It's the fraction of service I is receiving from a facility placed at j, if there's a facility. Okay? So again, you have equal to 1. I don't know what happens if you relax that to greater or equal 1, okay? Since fractions will not be greater than 1, I guess, or the percent of service received from j. Okay, so the next one is xij minus yj is less than or equal to 0. Yj is simply xjj, don't be confused by that. You might want to just, but yj's are 0, 1 variables, okay? The other ones are not. Again, summation yj, j going from 1 to n, is less or equal p, because they want to make it look like the fixed charge location, incapacitated facility location problem. Now, in one version, yj and xij are both 0, 1, which means that I is assigned to exactly one facility. Okay, it's a single assignment problem. But then sometimes you may relax xij to a continuous variable between 0 and 1, in which case you assign to multiple facilities and the cost dictates what to do. Okay, so now what do you do with the incapacitated facility location problem? All you do is the following. In the incapacitated facility location problem, let me do it here. That's not incapacitated facility location problem. That's actually the p-median problem with w's and dij's. So please change that. Which is not different from this, other than the fact that instead of Cij's, I used simply Wi dij's. All right. the incapacitated facility location problem. The objective function is different. I changed the order of summations. So in this case, the objective function is the sum of the transportation costs plus the fixed charges. Yj, if it's 1, it picks up the fixed charge of opening a facility at location j. To that, you add the cost of serving all possible demands from location j. Okay, xij is, if xij is 1, then cij is a picked cost. You sum that over all possible demands. That's the transportation cost associated with a facility at location j. So the term in the brackets would be the cost of having a facility at location j, and you sum that subject to the same constraints, except that this one is not in. You don't have it. So except for this constraint, you've got all the other constraints.
There is no restriction about how many facilities you are going to open.
That's right. That's right. And that's defined, or the model, when looks for an optimum solution, will decide how many to open depending on the fixed charges. So, as I said, what happens in the p-median problem is if you multiply this with a Lagrange multiplier lambda, the difference of the left and right sides, and add it as an extra term to the objective function, it will simply look like this, so that you can utilize whatever is available for solving this problem. Okay, that's the basic idea. Okay, I'm not going to go into any depth about the incapacitated facility location problem, because you probably covered that in your integer programming course, etc., because we are dealing with problems that take advantage of the network structure mostly. That's what I want to emphasize on, okay? So let me continue with P-center problem now. What do you think? Is P-center more complicated than P-median or not? Yes, no? I think it is more complicated. At least that's my feeling, yeah. Incidentally, even though I did not put it down on the board here, there's another formulation for the P-median problem that I just recently came up with based on actually looking for an optimal solution on spanning trees of the general network. The spanning tree problem, or the problem on a spanning tree or on a tree, is polynomial time solvable. And trying to look for a spanning tree that supplies an optimal solution, actually there's a theorem which myself and Burçin Bozkaya, one of my former students, we proved that there's always a spanning tree which supplies an optimal solution. However, the problem is there are so many spanning trees that you cannot really enumerate on such trees. So with that, looking for an optimal tree or a tree that supplies an optimal solution to the general network problem is non-trivial. It just turned out that while I was working on a delivery problem just recently, back in January this year, all of a sudden the formulation I came up with for the delivery problem turned out to suggest an interesting structure for a possible formulation for these problems, p-median as well as p-center. And so those formulations are very different compared to what you just have seen, which is the dominant formulation over the past 40 years or so. So we'll see how those formulations will actually compete with former formulations. Two of your classmates will be working on those formulations, and we'll see how they came up with, or with what kind of computational success they may come up with. Okay? One is Ataberk, and Pelin will be working on the center version of the same problem. So you still have a problem to choose, but then, for example, characterization of optimal trees might be an interesting problem. And you will be working on column generation for the p-center problem. John will not be working on anything because he's just auditing the course. Now, NS, he's working on somehow an interface of a planar location problem, or not planar, but there's a network embedded in the plane, and he's trying to actually locate detectors on the plane to cover somehow the network of interest. These are useful stuff or models for example, illegal crossing in the border, which we have a problem with in the, Iraqi, Syrian, Turkish border. We've got lots of terrorist activity going on, so you need to detect such illegal crossings, and that problem relates to that. So he will be working on that. Now, Hatice, what will you be working on? I haven't. Have you? You will. Okay. You will. You're still working on it. So you need to maybe in these days, maybe this week, you need to decide on somehow what you want to work on. Okay. I've got a number of problems that I can supply you with, if you couldn't come up with anything on your own. Okay. No problem. Okay. So let's now continue with p-center. Using the same notation as I had before, this time we have f function defined by the maximum of the distances rather than the sum of the distances. So I'm not going to repeat the notation, but you have a network under consideration, embedded network. You have, again, n vertices with weights. And f of x is defined by the maximum of the weighted distance between the points at x and vi, the vertex vi. You maximize over the vertices. This simply picks up, if wi are unity, then this simply picks up the largest distance of any demand point to a closest facility. So the largest of the closest ones. Okay? If you have weights present, they are just scaling factors, and you may use them at your liberty, as you wish, to somehow reflect additional considerations such as population density, etc., okay, at the vertices. All right, so we're trying to minimize this function, where the function definition is different, again, over all points x, which are, again, subsets of the network of interest with x having p points in it. The cardinality restriction again. That's the combinatorial formulation of the problem. Now, it turns out that this problem, at least what the literature has produced until now, does not look as easily grasping as the other one, the p-medium problem. Well, it's nevertheless still tractable in certain ways. The tree network case is still polynomial time solvable. The general network case is NP hard again. So it's computationally difficult. And one natural question to ask here is, when you wanted to find an optimum solution, an absolute p-center, well, it's an infinite search. The question is, can you restrict your search to a finite set without losing from optimality, okay? Without becoming suboptimal. So, a set x star, which is a subset of n with p points in it, is an absolute p-center of the network if the maximum weighted distance obtained by x star is no larger than the maximum weighted distance obtained by any other solution x. Okay. So that's the definition of an absolute p-center. And the question we address is, can we restrict our attention to a finite subset of the network from which at least one optimal solution comes? What do you think? Yes. Since I'm asking the question, I guess the answer should be a yes. Yes. Okay. And some of you have already looked into the literature on this, so you probably have a fairly good idea of what we're doing. Well, just think of the one-center case again, the absolute one-center, p equals 1 case. In that case, what did we do? We looked at an edge-restricted problem. On the edge, we looked at each distance, and each distance was piecewise linear with either a single piece or with two pieces. If it had two pieces, it looked like a housetop of some sort, right? That's what the distance looked like. Now, when you looked at many such weighted distances, then we're talking about the maximum of such distances. And so the maximum is a jagged or a piecewise linear function of some sort with dips and peaks. And it turned out that the single facility optimum occurs either at one of the endpoints of the edge or at a local point such as this one. Local optimal point such as that one. Now, you may have intersections of this sort Why do I refer to that as an intersection? Because that point is defined by the intersection of two piecewise linear functions, one coming from one vertex, the other coming from another vertex. You may have many such intersections. So this is just a very simple case. In which case, you're looking for an intersection point where deviation to the right or left makes you go upwards, okay, in the objective value. So you don't, whereas, for example, that sort of an intersection is not of interest for you because, that's interesting, yeah. Well, because, well, that one is lower than this, but nevertheless, there's a better one here, okay? Because here, when you, that's not a local optimum because when you go to the left slightly, you get better in the objective value. That's the idea here. All right, so with that, let's define such points as pairwise intersection points. We define a point x in N to be a pairwise intersection point if there are two distinct vertices I and j, well, vi and vj, such that the distance between vi and x is equal to the distance between x and vj with a deviation from x to towards vi or towards vj, not reducing the maximum of these two distances. Did that make sense? Let me see. So we have some sort of a distance coming from vi, which begins, for example, goes like this. The other one is, again, something like this. They could be coming down or not coming down. It doesn't matter. And in this case, this is the distance from vi to points in the edge, and that one is the distance from vj to points in the edge. And we're talking about an intersection point being a point of this sort, where a deviation that takes you either this way, closer to vj, or closer to vi, will not reduce the maximum of those distances. Okay? All right. So the theorem says that there is an optimal solution to the absolute p-center problem where each, let's give a name to it, there's an optimal solution x bar to the absolute p-center problem where each point xj in x bar, j going from 1 to p, is an element of the vertex set union with, say, P, where P is the set of intersection points. Of course, sometimes a given intersection point, a given pairwise intersection point may be defined by more than one pair, okay? Nevertheless, in the set P, it appears as a single point. The proof. I'm not going to go into it right now because we're just about out of time, but essentially you're doing exactly the same partitioning idea as you did in the p-median problem. And you're just using the new definition of f rather than the summation type definition. And you can work it out at home. Maybe next time I'll just go through it quickly, okay?